a packing crate with mass m equals 115 kilograms is slid up a 5-meter long ramp, which makes an angle of 20 degrees with respect to the horizontal by an applied force of F equals 1 times 10 cubed newtons. This is also equal to 1,000 newtons. Directed parallel to the ramp's incline. A frictional force of magnitude F equals 4 times 10 squared newtons resists the motion. If the crate starts from rest, what is its speed at the top of the ramp? So I'm going to quickly draw an illustration of what this might look like. So if we say that this is the ground, this is the incline, and this is at a 20-degree angle. I'm just going to put theta here for now. Say that this dot represents the crate. So perpendicular to the incline, we have the normal force that keeps it up. Pushing it up parallel to the ramp, we have big F, the force, the applied force. And opposing that, it's the frictional force, or little f. And then, of course, pulling it straight down is the force of gravity, or mg. These arrows are a little disproportionate, but I'm going to make this one slightly bigger for now. So from that, you can kind of decompose this into its other vectors. This might be a little hard to see, but decompose it into the vector that pulls it straight down and slightly across. So that would be what it would kind of look like. And so this one is the one that we're focused on. So if this is mg and this is the angle theta, then this would be mg times the sine of theta. And this would be acting parallel to the ramp, and the same as the frictional force. Might be better if I draw it the other way instead. Something like this. That probably looks a little better. So this is mg, this is mg sine theta, and this is mg cosine of theta. The cosine part of theta, this angle here, is the part that is perpendicular to the inclined surface. So we need to look at this part because it's acting in the same direction as the force of friction and is parallel to the surface of the ramp. So now we can use Newton's second law that says that the summation of all the force, or the net force, is equal to the mass times acceleration of the crate. So let's figure out what the net force is. So in a force acting parallel to the ramp that's going up, we have the applied force. And then acting in its opposite direction, we have the force of gravity, one part of it, and the frictional force. G sine theta equals ma, and that equals the mass times acceleration. Again, these two are both subtracted because this is opposing the applied force, and mg sine theta is also acting in the same direction as the frictional force, which opposes the applied force. And now we just need to solve for acceleration, and then we can just divide by mass. So we get that the acceleration is equal to the applied force minus the frictional force minus mg sine theta divided by the mass. And then we can just plug everything in to find the acceleration. So if we plug everything in, equal to the applied force of 1,000 newtons, 1 times 10 cubed is 1,000 newtons. The frictional force of 400 newtons, 4 times 10 squared is 400, minus its mass of 115 kilograms times 9.8. This is a little squished, so I'm a little out of room. So I'm going to write it somewhere where I have more space. Maybe down here. And this is the exact same thing, times 9.8. And then we'll multiply that by the sine of the angle, 20 degrees. We're going to divide that by the total mass of 115 kilograms. And now you should get that A is about 1.87 meters per second squared. So that's what we got for now. So that's the first part. But it's not asking for the acceleration, it's asking for the speed at the top of the ramp. So we know that the acceleration is about 1.87 meters per second squared. Now we just need to figure out the speed at the top of the ramp. To do that, we can use our kinematic equations, as we know that it is slid up a 5-meter ramp. So we have enough variables for at least one of them. We have that the displacement is equal to the initial velocity times time plus 1/2 times the acceleration times time squared. The change in x, the displacement, is equal to the average of the initial and final velocities times the time interval. Then you have the final velocity is equal to the initial velocity plus the acceleration times the time interval. And finally, you have that final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. So if we look at our equations, we'll notice that we don't have a time interval given to us, and we did not calculate the time it took for this box to be pushed up. So all 3 of these equations can be eliminated, all 3 of these other ones, because we don't have a time interval that we can use. So this leaves us with the last equation that says that the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. And we're solving for the final velocity. Now we know that the initial velocity is 0, so the initial velocity squared is still 0. 0 squared is still 0 because it starts from rest. And then, so we just get that the final velocity squared is equal to 2 times the acceleration times the displacement. And we can just square root that to get the final velocity. And now we just need to plug everything in. Go to the square root of 2 times the acceleration of about 1.87 meters per second squared times the displacement of a 5-meter long ramp. And now if you solve this, you should get that the final velocity is about 4.32 meters per second. And that is how you would solve this problem here.